Hello everyone, I am Shivani and welcome to Civil series. So this video is about the short notes of theory of structure, and this theory of structure is fully based on BMC syllabus of sub-engineer and junior engineer. So in this video we'll cover each and every important point from theory of structure as per the short notes. So let's start with the video first. So first we start with the syllabus. So in the theory of structure, analysis of beam is there, analysis of beam, frame and trusses. Then slope deflection method and moment distribution method. These are the two methods in the theory of structure. Okay. So first we start with the classification of structure. Classification of structure is divided into two types. First is on the basis of dimension and second is on the basis of joint. So we'll see first on the basis of dimension. Okay, so you all know there are two type of dimension, 2D and 3D. Okay, there are two type of dimensions, 2D and 3D. So first we go with a 2D structure. First we go with a 2D structure. 2D structure is also known as plane structure. 2D structure is also known as plane structure. In case of 2D structure, there are three unknowns. Okay, there are total number of unknowns in 2D structure are 3, and in that 3, 2 are linear unknowns. 2 are linear unknowns. Linear forces are 2. Okay, and angular forces 1. Angular forces 1. So which are the linear forces and which are the angular forces? So linear forces are f of x and f of y, and angular forces movement. Okay. Similar in case of 3D structure. So 3D structure is also known as the space structure. Okay. 2D plane structure and 3D as a space structure. In case of a 3D, total number of unknowns are 6. Total number of unknowns are 6 and the linear force is 3 and angular force is 3. Okay. So here linear forces are f of x, f of y and f of z. Then similarly m of x means movement, m of y, m of z. So these are the linear and angular forces in case of 3D structure. On the basis of dimension, 2D and 3D. 2D known as a plane structure, 3D known as a space structure. 2D consists of 3 unknowns, 3D consists of 6 unknowns. In 2D, linear are 2, angular is 1, and in case of 3D, linear are 3, angular are 3. Then second, on the basis of joint. On the basis of joint, there are 4 structures or 4 structures. In that, first is simply supported structure. Simply supported structure. Then second is pin jointed structure. So pin jointed structure also known as trusses or truss structure. Then third is rigid jointed structure. Rigid jointed structure is a frame structure. Rigid jointed structure is a frame structure, and last one is grid structure. Grid structure. So these are the 4 structures which are classified on the basis of joints. So in that, first is simply supported, second one is pin jointed structure or truss, and third one is rigid jointed structure and frame structure, and last is grid structure. Okay, then next point is type of support for 2D and 3D structure. Okay, so there are 4 type of supports. First we see it for a 2D structure. So for 2D structure, first support is guided roller support. Guided roller support. So guided roller support is, so this is the guided roller support. First, the guided roller support is in a vertical direction, called it as a vertical guided roller support, and second one is in horizontal direction, and this is known as a horizontal guided roller support. Okay, so this is vertical guided roller support, and then second is horizontal guided roller support. So this vertical guided roller support example is shutter. Okay, shutter of stores. So this is the example of vertical guided roller support, and this support is allowed to move in a vertical direction. Okay, means that vertical value is not present here. Okay, because it is allowed here. And horizontal and movement, there is restriction for these two values, so these values are present here. So this is the kind of reactions act on this vertical guided roller support. Then in case of horizontal, this horizontal guided roller support example is gate. Okay, that gate is present on entrance of our house. That kind of a gate is horizontal guided roller support, is with the horizontal guided roller support. And this gate has, or this support has only horizontal direction movement. Okay, it move only in a horizontal direction. That's why the horizontal value, horizontal force value is not present here, but the vertical and movement value is present here, means it is prevented in a vertical and movement. Okay, so these are the values for guided roller support. Then next supports are roller support. So roller support is, this is how we represent the roller support. So this roller support is with a vertical force. Okay, so here vertical force is present, means this roller support is not allowed to move in a vertical direction, means for the vertical the value is present, and for horizontal and movement values are not present. Okay, then next third is hinge support. Hinge support, so this is the hinge support. This hinge support is with a vertical force and horizontal force, means the value of vertical and horizontal, both the values are present here and movement is not present here. Then fourth, fixed support. So fixed support, so this is how we represent the fixed support: horizontal, vertical and movement. Here horizontal, vertical and movement, all the three values are present, means this fixed support is restricted in all the three direction, or all the two directions and movement, the restricted in case of a fixed support. So these are the values for 2D structure. Then we'll see for a 3D structure. Okay, then in case of a 3D structure, so this is how the 3D diagram. Okay, so here x, y and z, hx, hy and hz, these are the movements here, mx, my and mz. Okay, so first guided roller support. First is guided roller support. First is vertical guided roller support and second is horizontal guided roller support. Vertical guided roller support is allowed to move in a hx, hy, mx, my and mz. These are the values which are not allowed, or these are the values which are prevented in case of a horizontal guided roller support, means values are present here. And that allowed in case of a Vy. So here correct it Vy. Okay. Then in case of a horizontal guided roller support, these values are allowed in case of Hz, Vy, then Mx, My and Mz. Okay. Here values are present, and values which is not present here is Hx, is allowed in that direction. Then second, in case of roller support, this roller support is only restricted in case of a vertical direction, in case of vertical direction movement. So that's why Vy is present here, and the remaining values which are Hx, Hz, Mx, My, Mz all are not present here. Then third is hinge support. Hinge support is allowed to movement only in case of a movement, and it is restricted in a horizontal and vertical forces. So here the values of Hx and Vy are, and the one more value which is Hz is also present here, and remaining Mx, My, Mz values are not present here. Then last one is fixed support. So in case of fixed support, the all values are restricted here. All movements, all forces are restricted. So that's why all the values are present. mx, my and mz. Okay, these all values are present here. Okay, here one thing is important, that remember, if in case of any support there is a allow of any direction, there is allowment of any direction movement, okay, then the value is absent there. Okay, because there is a no restriction as a value. And if there is a restriction of any kind of force on any kind of support, then that value, the value of that force is present there. Like in case of roller support, vy direction movement means vertical movement is not allowed, means there is a one value which is not equal to 0. That's why I correct it as or take it as correct, because this value is present. But in case of hx, hz, mx, my and mz, values are not present, means these values are equal to 0. Okay, these values are equal to 0. That's why this roller support is allowed to move in these kind of directions. Okay, so this is how the concept here, and these are the 2D and 3D structures, and with their forces and movements. Then determinacy and indeterminacy. Okay, so before discussing this, first we discuss about the static equilibrium equation. Equilibrium equation. Okay, so there are three equations: f of x equal to 0, summation of f of y equal to 0, and summation of moment equal to 0. Okay, so here first determinacy, second is indeterminacy. If any kind of beam, truss and frame is solved by the help of these static equilibrium equations, then that structure is known as determinacy. Means solved by summation of f of x, summation of f of y and summation of moment. And here not solved by, not fully solved by. Okay, some few values are solved by these equations, but some values are remain to solve, then this is considered under the indeterminacy. Okay, then there are few examples related to determinacy. First is three hinged arch. Second is simply supported beam or simply supported structure. Then third is overhanging beam, and last one is cantilever beam. Okay, these are the examples for the determinate structure. Then the examples for indeterminate structure. First is two hinged arch. Then second is fixed arch. Second is fixed arch. Then third is redundant arch. Then fourth is fixed beam. And then next fifth is continuous beam. And next is sixth number, propped cantilever beam. Okay, so these are the few examples which are related to determinate and indeterminate structure. Okay, and here in the exam they ask about the 3 hinge arch and 2 hinge arch, because these examples are confused that which is determinate and which is indeterminate. So that's why these two are important. Mark it as important. Okay, two hinge arch is under the indeterminacy and 3 hinge arch is under the determinacy. Okay, the next point. Then next, on the basis of indeterminacy, there are two types. First one is static indeterminacy and second is kinematic indeterminacy. Static indeterminacy is represented like this, ds, and kinematic indeterminacy is represented like dk. Okay, then static indeterminacy is divided into two types. First one is external static indeterminacy and second is internal static indeterminacy. Okay, first is external, second one is internal. So ds is external static indeterminacy plus internal static indeterminacy. Okay, addition of these two is nothing but a static indeterminacy. External static indeterminacy is represented by ESE or DSE, and internal static indeterminacy is represented as DSI. So here ds is equals to DSE plus DSI. This is the formula for static indeterminacy. Okay, and we'll see the static indeterminacy and kinematic indeterminacy in detail in further video. Then next is external static indeterminacy. So this is the part of static indeterminacy. One part is external static indeterminacy and second part is internal static indeterminacy. In that first, external static indeterminacy is represented like this, that DSE. So formula for DSE is DSE is equal to RE minus 3 for 2D structure and DSE is equal to RE minus 6 for 3D structure. Okay, so here the RE is total number of unknown reactions. Total number of unknown reaction is equal to RE, and then if the value of DSE is greater than 0, okay, if you calculate this and you get the value of DSE greater than 0, then that structure is externally indeterminate. Externally indeterminate. And same in case when DSE is less than or equal to 0, then that structure is externally determinate structure. Okay, externally determinate structure. Okay, so formula is DSE is equal to RE minus 3 for 2D and RE minus 6 for 3D. RE, from where you calculate that RE. So for example, this is the simply supported beam. Okay, and this simply supported beam, here for this simply supported beam is 2D. Okay, to calculate the DSE of this beam, so DSE, here the reactions are 1 second, and here one more reaction, here horizontal reaction is there, so 3 reactions are there. Okay, so 3 minus 3 equal to 0. For this particular example, 3 minus 3 equal to 0. So here the value is equal to 0. So here this condition is happens, means this structure, this simply supported beam structure is externally determinate structure. Okay, that's how you calculate the DSE. Okay, then next there are some special condition in case of external determinacy. So that cases are, first case is if there is any fixed beam. Okay, if there is any fixed beam and that fixed beam is acted by a point load, and because of that point load, the here on this beam only vertical reactions are acted. So because of that vertical reaction, there is a no horizontal reaction. So you can take the value of DSE as here as replace this 3 with 2 because only 2 equilibrium conditions are required here. Okay, if you calculate by this formula, then you get a same value, but this is the condition when there is any point load, you take 2 as the unknown equilibrium equations or two number of equilibrium equations, and the total number of unknown reactions are here. Here horizontal, you neglect the horizontal here, so that's why 2 from this side, 2 from this side, so you get 4. So this is equal to 2. Okay, so if fixed beam is subjected to point load, then that beam or that beam is externally indeterminate by 2 degree. Okay, and same if the fixed beam is subjected to incline loading or no loading, then that beam is externally indeterminate by 3 degree. Okay, these are the two MCQs which asked in an exam, so these two are important. If fixed beam is subjected to point load, then that beam is externally indeterminate by 2 degree, and if fixed beam is subjected to incline loading or no loading, then that beam is externally indeterminate by 3 degree. Okay, here indeterminate by 3 degree. Then next internal static indeterminacy, that represented by DSI. Okay, so there are two formulas for DSI. DSI is equal to 3C minus RR, and DSI is equal to 6C minus RR. This is for 2D structure and this formula is for 3D structure. Okay, so here C is number of closed loop. Okay, you can change this C as a C dash, and that C dash is a number of cut required to make structure close to open. Okay, here C and C dash are equal. Okay, for example, you take example here. So this is the frame. Okay, this is one of the frame, and this is the closed loop. Okay, so here take C as 1 because this is a one closed loop. Okay, and C dash is number of cut required to make the structure close to open. Okay, if you cut this line, then you get a open loop. Okay, so that's why C dash is equal to 1 because one cut is required. So here C is equal to C dash. You can take C here or C dash here. The value or the last answer is same. Okay, then RR is the internal releases. RR is the internal releases present in a structure. Okay, we'll discuss that internal releases in the video further. And then next, this condition. Okay, mainly this condition is for beam or frame. Okay, this condition is for beam or frame. Okay, here I write RR is equals to internal releases. Then next conditions are for trusses and pin jointed structure. Okay, this condition is about the beam and frame. Next condition is about the trusses or truss structure or pin jointed structure. And formulas for that are DSI is equal to M plus 3 minus 2J, and second DSI is equals to M plus 6 minus 3J. This is for 2D and this formula is for 3D. Okay, M is the member, J is equal to joint, and both are formulas for 2D and 3D structure. Okay, these formulas are for truss and pin jointed structure. These formulas are for beam and frame structure. Then some important points. Okay, these are 4 formulas which are important. If you solve any kind of a numerical, and if you want to solve that numerical directly, okay, to decide whether that structure is determinate and indeterminate, statically determinate or indeterminate, so you can use these formulas also. So for pin jointed structure, for pin jointed plane structure, or pin jointed plane structure to be statically determinate. Okay, if the structure is statically determinate, means ds is equal to 0, you can directly use this formula. M plus r minus 2j equal to 0, 2d, and m plus r minus 3j equal to 0 for 3d. Both the formulas are for truss or pin jointed structure. Then next, 3m plus r minus 3j equal to 0 and 6m plus r minus 6j equal to 0. This is for 2D and this is for 3D. Both formulas are for rigid frame. Okay, then next important thing is two names for there is another name for indeterminate and determinate structure. Indeterminate is also known as hyperstatic. Hyperstatic. Okay, indeterminate is also known as hyperstatic, and then determinate is known as hypostatic. Okay, these are few important points. The next is internal release in static indeterminacy. Okay, so you all know that RR is the internal release as we seen in the formula of internal static indeterminacy. So internal release is RR. So first for internal hinge, so this is how we represent the internal hinge. This is the beam and this is the internal hinge. Okay, so this is the internal hinge, and RR value for internal hinge is equal to 1. Then next for internal roller, so this is the internal roller. This is the internal roller, and value of RR is equal to 2. Then next internal horizontal guided roller, so this is the internal horizontal guided roller, and RR value is here, RR equal to 1. Okay, RR is equal to 1. Then next internal vertical guided roller, so this is the internal vertical guided roller, and value of RR here is also equal to 1. RR is equal to 1. Then the internal horizontal release, the internal horizontal guided release is also known as axial release, and internal vertical guided roller is also known as shear release, Okay, then next and last, which is very important, that internal hinge provided at joint or at junction, so this is the junction which is present in any kind of frame and truss. So this is the junction, present in the frame, and here on this junction, three members are meet. Okay, so M dash is equals to number of member meeting at internal hinge. So this is the M dash, and formula to calculate the internal release for this is RR is equals to M dash minus 1. Okay, so here for this junction M dash is equal to 3 and RR is equals to 3 minus 1 equal to 2. Okay, so this is how the internal release in static indeterminacy. Then internal release in kinematic indeterminacy. This is also represented by RR. Okay, so this is internal release, and internal release here the same conditions are there as first we see in the static indeterminacy. So here the value is degree of freedom. Okay, one value is internal release and another value is degree of freedom. So degree of freedom is 4 for internal hinge, for internal roller, next for internal horizontal guided roller, and internal vertical guided roller. Okay, you can use this to solve the kinematic indeterminacy. Okay, you can only use the degree of freedom to solve the kinematic indeterminacy. Okay, this is first method. Okay, and then next is, this is a junction or this is a joint. Okay, here M dash is the number of member meeting at junction. Okay, So here RR value is equals to M dash plus 2. M dash plus 2. Okay, so this is the junction and number of members are, this is first member, this is second, and this is third member. Okay, so M dash is equals to 3 plus 2 equal to 5. So here for this junction RR is equals to 5. Okay, so you can solve by this method also. So this is the second method. Okay, to find out the internal release, this is the first method and this is the second method. Then we'll see how to use these internal releases in original kinematic indeterminacy formulas. Okay, then next is then kinematic indeterminacy. First we'll see kinematic indeterminacy formulas for 2D beam or frame. 2D beam or frame. Okay, so here first for a rigid frame or rigid joint. First for rigid joint. Second is for roller support. Second is for roller support. Third for hinge support. Third for hinge support. Then fourth for fixed support. Fourth for fixed support. Okay. So here the degree of freedom is equal to 3. Then next for roller, degree of freedom is equal to 2. For hinge, degree of freedom is equal to 1. And for fixed support, degree of freedom is equal to 0. Okay. Then similarly, the degree of freedom for the vertical guided roller support and last horizontal guided roller support. So degree of freedom is 1 for both of vertical and horizontal guided roller support. Okay, here this is the one condition. You can solve the kinematic indeterminacy with the help of degree of freedom, and then next is with the help of formula, which is dk. Okay, degree of kinematic indeterminacy is represented by dk. dk is equals to 3j minus re plus rr. Okay, j is the joint, number of joint, re is the number of unknown reaction, and RR is the internal release. Okay, for kinematic indeterminacy, internal release is calculated by M dash plus 2, internal release. Okay, we'll see one numerical for this kinematic indeterminacy to differentiate how to calculate that dk or kinematic indeterminacy by degree of freedom, and next by this formula. We'll see one example. So here we see the example of kinematic indeterminacy. First example, this is the frame, rigid frame with fixed support. Okay, so first we solve with the help of a degree of freedom. So for degree of freedom, for fixed beam is 0, for fixed support is 0. For this rigid joint, okay, so this is the rigid joint. We call it as a rigid joint. So here the degree of freedom is 3 and here degree of freedom is 3. Okay, so add all the degree of freedom, 0, this 0 plus 3 plus 3 plus 0 is equal to 6. Okay, so degree of freedom is equal to 6. Next, take the similar diagram here. We'll solve it again with the help of formula. So this is the frame and formula is dk is equals to 3j minus re plus rr. Okay, then 3j joints. First, this is the first joint, this is second joint, this is third joint, and this is fourth joint. 3 into 4. Okay, minus re is unknown reactions, so this is fixed beam. Here is also fixed beam. 3 reaction for this support, 3 reaction for this support, minus 6 plus there is no internal hinge support present in the given frame. Okay, if there is this kind of internal hinges present in this frame, then you can take the RE as m dash plus 2. Okay, then you take R is equals to m dash plus 2. Here two members are connected, first and second, so 2 plus 2 equal to 4. Okay, if internal hinge is present, but in this particular diagram there is no internal hinge, so that's why I take RE as 0. Okay, solve this. 12 minus 6 equal to 6, so dk is 6. Okay, so if you solve with the help of degree of freedom, the value is same. With the help of formula, the value is same. If you solve with the degree of freedom, you get answer easily, so I prefer you go with the degree of freedom value to solve the numerical. But to knowledge and to find out the values of RE, RR and J, so this formula is also important for the MCQ point of view. And for the numerical point of view, degree of freedom is easy method to solve the question. Then next is then kinematic indeterminacy for 3D structure. Okay, 3D structure in case of beam and frame. 3D structure in case of beam or frame. Okay, in that first is rigid joint. Rigid joint. For rigid joint, the degree of freedom, rigid joint is like this. This is the rigid joint. Okay, in case of frame or beam, and degree of freedom for this rigid joint is 6. Then second is a roller support. Roller support, and for roller support, the degree of freedom is 5. Then third, for hinge support. For hinge support, degree of freedom is 3. And last is fixed support. For fixed kind of support, the degree of freedom is 0. Okay, so these are the degree of freedoms for different kind of supports in 3D structure, and one formula is there. Okay, you can solve the kinematic indeterminacy dk with the help of this degree of freedom, or you can solve the degree of freedom with the help of this formula. Whichever is easy for you, you can choose that. Dk is equals to 6j minus re plus rr. Okay, RR is the internal release for kinematic indeterminacy. RE is the unknown reactions present, and J is the number of joints. Then next. So here we solve one numerical which is related to 3D frame structures, and this is an example. First we solve by using the degree of freedom, and then we solve the same numerical with the help of formula. Okay, so here first the degree of freedom for rigid joint is 6, 6 and 6, and here is also 6. Okay, then degree of freedom for fixed support 3. Sorry, degree of freedom for fixed support is 0. For fixed support is 0. Here for rigid joint 3, and for the roller 5. Okay, add all the degree of freedoms. dk is equal to summation of degree of freedom. 6 plus 6, 6. 6 plus 3 plus 5 plus 0 plus 0. This is equal to 32. Okay, so degree of freedom at dk equal to 32. Okay, then we solve with the help of formula. So formula for dk is 6j minus re plus rr. Okay, here internal release is not present, so rr value is equal to 0. Okay, then joints. So here this is first joint, second, third, fourth, fifth, sixth, seventh and eighth joint. So 6 into 8 minus RE, number of reactions. So for fixed support in case of 3D structure, okay, in case of 3D structure, so the fixed support reactions are 6. In case of hinge, 3 reactions are there. In case of roller, 1. And in case of fixed, 6 reactions are there. So add this 6 plus 3 plus 6 plus 1. RE equal to RE equal to 16. RE equal to 16 here. So take 16 here. This is 48 minus 16. So here dk is also equal to 32. Okay. So values of dk are same if you solve with the help of formula, or you can solve with the help of degree of freedom. Whichever the method is easy for you, you can adopt that method. So I suggest go with the degree of freedom because it is easy to solve the dk value, and for the ds go with the formulas. Okay. Then next the kinematic indeterminacy for truss or pin jointed structure. Truss or pin jointed structure. Okay. Truss are the structures which is always truss are the structure which always carries axial load. Which always carry axial load, no movement and no rotation. No movement and no rotation is there in case of trusses. Okay, so here the degree of freedom for pin joint is okay, so degree of freedom for pin joint is equal to 2. Then for hinge support, degree of freedom is also equal to 2. Then for roller support, degree of freedom is equal to 1. Okay, these are the degree of freedoms. Then next formulas to solve degree of freedom is 2j minus re plus rr, and second one is 3j minus re plus rr. First is for 2D and second is for 3D structure. Okay, so this is how you can solve the degree of freedom, and this is how you can solve the kinematic indeterminacy for truss or pin jointed structures. Then there is one special case. In that special case, when members are inextensible or axially rigid. Okay, so we'll see that condition too. Then kinematic indeterminacy for the members which are inextensible. Okay, members which are inextensible or extensible or axially rigid. Okay, inextensible means what? So inextensible means member does not elongate. Member does not elongate its along its length or axis. Okay, the members which does not elongate along its length or axis, that members are nothing but inextensible members or axially rigid members. Okay, so here n dash is a number of inextensible member. So in the numerical sometime they mention that 3 members are inextensible or 2 members are inextensible, or else each and every member is inextensible. Okay, so for that you need to add n dash into the formula. So how to add that? So dk is equals to 3j minus re plus rr. Okay, so this is the formula for 2D structure in case of beam and frame. So to calculate this dk, just minus this n dash. Okay, in case of 2D. And same if in case of 3D, 6j minus re plus rr, just minus n dash from this formula. So you get the formula for 3D beam and frame in case of the members are inextensible. Okay, this is also important formula. Method to analyze indeterminate structure. There are two methods. First one is force method and second is displacement method. In case of force method, the degree of static indeterminacy is less than degree of kinematic indeterminacy. But in case of displacement method, degree of kinematic indeterminacy is less than degree of static indeterminacy. Okay, this is the major difference between two methods. Then next, redundant is treated as unknown parameter in case of force method. Okay, and here in case of displacement method, displacement is treated as unknown parameter. Displacement is treated as unknown parameter. Okay, next there are few methods in force method. In that, first one is method of consistency. Method of consistency, also known as method of deformations. Okay, second is strain energy method. Strain energy method. Then third one is flexibility method. Flexibility method. Then column analogy method. Fourth is column analogy method. Then next is three movement method. Three movement method. And last one is unit load method. Okay, last one is unit load method, and this unit load method is also known as method of virtual work. Method of virtual work. Okay, then in case of displacement method, there are four methods. In that, first one is movement distribution method. Okay, movement distribution method. Then next is slope deflection method. Slope deflection method. Then next method is stiffness method. Okay, stiffness matrix method. Stiffness matrix method. And last one is Carney's method. Carney's method. So these are the methods used to find out the redundant, which is unknown parameter in case of force method, and displacement, which is unknown parameter in case of displacement methods. Okay, all the methods are important. They ask one question about these methods is that this first point, which is ds is less than dk in case of which method, and next is, or similarly in case as a dk is less than ds is happens in which method, and also ask a redundant parameter. And few methods they ask that method of consistency is belongs to which method, or else they ask the moment distribution and slope deflection method belongs to which method. Okay, these kind of questions that they ask on these points. The next point is stability or instability. There are three type of stability or instability. In that first one is externally stable or unstable. Okay, externally stable or unstable. So externally unstable and stable, there are two conditions. First one is linear stability or instability. Okay, and second is angular stability or instability. Okay, so in case of linear stability, if all external reactions are parallel to each other, okay, then the structure is externally unstable. Okay, if all reactions are parallel, then externally unstable. If all reactions are not parallel to each other, then that structure is externally stable. Okay, for example, this is simply supported beam. Okay, roller support at first end and roller support at second end. Okay, this is one of the simply supported beam with two roller supports. So the roller support is with the vertical reactions, and both the vertical reactions are parallel to each other. Okay, if you extend this, then both the vertical reactions are parallel to each other. So this structure is externally unstable. Okay, and similarly in case of angular stability or instability, if all reactions are concurrent to each other, then that structure is externally unstable. Okay, concurrent means what? That all reactions are meet at single point. Okay, meet at single point or a same point, then that is the concurrent. And if all reactions are concurrent, then that structure is externally unstable. Okay, for example, this is simply supported beam with roller support at one end, and take here a inclined roller support. Okay, so in this particular beam, the A reaction and B reactions are not parallel to each other. So this is linearly stable. Okay, but both the reactions, if we extend this, then both the reactions meet at some point. After extending it, meet at some point. Okay, so both the reactions are not concurrent to each other. Both the reactions are concurrent to each other. Okay, both the reactions are concurrent to each other. That's why this structure is externally unstable structure. Okay, then next B is internally unstable or stable structure. Okay, if member provided, okay, there are number of members here. One member is there. If this is a frame, okay, if this is a frame, so in the frame this is first member, this is second, and this is third member. Okay, if member provided is less than member required, then that structure is internally unstable. Okay, and next condition is if member provided is greater than or equal to member required, then this is condition of internally stable structure. Okay, then next condition is, then third is overall stability or instability. Okay, so this overall stability is based on external and internal stability or instability. Okay, if the structure is externally stable, and internally unstable, okay, internally unstable, then overall structure is overall unstable. Okay, next, if structure externally stable and internally stable, then the structure is overall stable. Okay, then next, third, if structure is externally unstable and internally stable, then the structure is overall unstable. Okay, and fourth is if structure is externally unstable and internally unstable, then this is overall stable. No, this structure is not overall stable. This structure is also overall unstable. Okay, so only condition is here that if both external internally are stable, then only that overall structure is stable. So here we'll see about the next topic from TOS, which is truss. And truss is a structure which is made by a number of triangles, and on the truss the loading is act only on the joint, and the truss structure always carry axial load. This truss structure always carry axial load. Okay, and there are few types of these trusses depend upon the different criterias. In that, first is perfect truss. Okay, then next is redundant truss, and last one is deficient truss. Okay, we'll see the three of the trusses one by one, and on the basis of classification there are two types. First is 2D or plain truss, then next is 3D, second 3D or space truss. Okay, here we see only about the 2D truss. So in case of 2D truss, first truss is simple truss, then second one is complex truss, and third is compound truss. Compound truss. Okay, so these are the three types of trusses, and we'll see these three trusses one by one. So here the analysis of determinate structure. So first, in case of analysis of determinate structure, type of trusses we'll discuss. Okay, type of trusses. So there are three type of trusses: perfect truss, redundant truss, and next is deficient truss. Okay, first condition, if ds value means static indeterminacy is equal to 0. Second, if ds is greater than 0. And third condition is if ds is less than 0. Okay, there are three conditions. We'll see the three conditions one by one here. Okay, first, ds is equal to 0 means member provided is equal to member required. Member provided is equals to member required. How? So by the formula m is equal to 2j minus 3. If this 2j minus 3, if this 2j minus 3 is equal to the member provided, then this condition is followed. Okay, if this condition happens, then that structure is determinate. That structure is determinate and stable structure. Okay, that structure is determinate or stable structure. Okay, and if the structure determinate and stable, and if member provided are equal to member required, m is equals to 2j minus 3 and ds value is equal to 0 if all the four conditions, follows. Okay, these all are depend on each other. If all follows, then this truss is known as perfect truss. This known as perfect truss. Okay, the next condition is if ds is greater than 0. If ds is greater than 0, then member provided is greater than member required. Okay, obviously. And the next, members are greater than 2j minus 3. J is the number of joint, m is the member or number of members. If this condition happen, then that structure is indeterminate. Then that structure is indeterminate and stable. Indeterminate and stable. If this condition follows, then that truss is redundant truss. That truss is redundant truss. Or this truss is also known as over stiff truss. Okay, this truss is also known as over stiff truss. Then next is ds is less than 0. If ds is less than 0, then member provided is less than member required. Member provided is less than member required, and that number of members are less than 2j minus 3. Then that structure is determinate. That structure is determinate and unstable. Okay, if this condition follows, then that truss is known as deficient. Then that truss is known as deficient truss. Okay, so these are the three trusses and these are the conditions to know the type of truss. Okay, so this is the analysis of determinate and indeterminate trusses. The next method of analysis of determinate structure. Okay, so there are four methods to analyze the determinate structure. First method is method of joint. Next is method of section. Third is graphical Willard-Morse method, and last one is bar chain method. Okay, so here in this two methods are majorly used. So first is method of joint and next is method of section. Okay, so we'll see the two methods one by one. Then first method is method of joint. This method of joint is used when force are to be calculate in each and every member. Okay, if force are to be calculated in each and every member, then we use the method of joint. In that, to calculate the external reaction, and second to calculate the internal reaction, we use here for external reaction calculation we use static equilibrium equation, and for internal reaction calculation we use joint equilibrium equation. Okay, so in case of static equilibrium equation, there are three unknowns values are there, or three equations are there to find out the unknown values. First one is summation of f of x equal to 0. Second is summation of f of y equal to 0. Then next is moment or the summation of moment equal to 0. Then joint equilibrium equation, summation of f of x equal to 0, summation of f of y equal to 0. So these are the two equations here and these are the three equations here as a static equilibrium equation, and here joint equilibrium equation is used. The next method is method of section. So this method, in that how to choose section. First we'll decide how to choose a section to calculate the unknown forces. First, section passing through those members. First, section passing through those members, those member in which forces are to be calculated. Okay. Next, section cut. If section cut, three unknowns should be formed. Three unknowns are to be formed. And third is section is vertical, horizontal, incline and zigzag. Okay, these kind of sections you can form. Then this method of section is used when the forces are to be calculated. The forces are to be calculated for some member, for some members or one member. Okay, for one member and for some members you can use the method of section. But in case of method of joint, you can use that method when forces are to be calculated in each and every member. Okay, so here to calculate the external reaction, and to calculate the internal reaction, for both calculation we use here a static equilibrium equation. There are three equations in that: summation of f of x equal to 0, summation of f of y equal to 0 and summation of moment equal to 0. Okay, so this is how the method of section. Then concept to identify number of zero force member in truss. There are two concepts. First concept is if on the joint two forces are act. Okay, this is first force, this is second force. Two forces are act, and on the same joint third force is act. Okay, on the same joint third force is act. And if there is no external force acting on this joint, okay, this is important, no external force acted. Okay, then and then only this force or this member is turned to be 0. Okay, then and then only this force or this member is turned to be 0. The next condition is if these kind of two forces, okay, if this angle is increased by some amount, then it's okay. And if this kind of a members are acted in the truss and no external reaction, okay, here the same condition applies, no external reaction acted, then and then only both the forces are 0. Okay, both the force members are turned to be 0 here. So these are the two important concepts to identify the zero force member in the truss. Here the point is moment distribution method. Okay, let's take one example here. So here this is a structure. Okay, you can say it as a frame structure. This is support A, B and O. If we apply a moment at joint O, this is M. If we apply a moment at joint O, then moment distribution on member OA and OB. Okay, OA is one member and OB is the second member. Moment distribution on both members in that EI, okay, this is flexural rigidity of OA is greater than flexural rigidity of OB. Okay, that is if this happens. Okay, that is if this happens, that is the member OA is more stronger and stiff, more stronger and stiff. Okay, and then according to MDM movement distribution method, if member is stiffer, then that attracts more movement. Okay, that attracts more movement. Okay, then the movement in case of OA member is more than the movement in the member OB. Okay, this is the physical meaning of the MDM movement distribution method. Okay, this is how it goes. If the EI means flexural rigidity of any member is larger than the EI. Okay, so this is an example. If we take the value of the I is here 2I and take I as here I value is I, then this is an example. Okay, here 2I is more than the I. Okay, so this happens here. This EI is automatically increased than the EI of OB. Okay, so the movement in case of the member OA is larger than the OB, as that member OA is more stiffer and more stronger. Okay, stiffness. Stiffness is represented by K. Okay, stiffness is represented by K, and stiffness is the value or the movement produced by unit deflection or unit rotation. Stiffness is the value of load or movement. Stiffness is the value of load or movement that produce unit deflection. Okay, that produce unit deflection or unit rotation. Okay, there are two type of stiffness. First stiffness is axial stiffness, and second stiffness is bending stiffness, Okay, so here the load and moment value distribute here. Okay, so the value of load which produce unit deflection in case of axial stiffness, and value of movement produce unit rotation here in case of bending stiffness. Okay, so the formula for stiffness is K is equals to axial stiffness is equals to AE by L. Okay, this is the axial stiffness, and AE is nothing but axial rigidity. Okay, then for bending stiffness there are three conditions. In that, first one is if far end is fixed. If far end is fixed, then K value is equals to 4 EI by L. If far end is hinge or roller, then K value is equal to 3 EI by L. Third, if far end is free, then K is equal to 0. These are the three values of stiffness for different end conditions. Okay, so this is how the two types of stiffness, bending and axial stiffness. Okay, these are the formulas. Okay, so write these formulas. These are the important formulas. Here the EI is equals to flexural stiffness, or you can say it as a bending stiffness. Then next we'll see the stiffness at joint. Okay, so here we see about the stiffness at joint. Okay, stiffness at joint. Stiffness at joint is represented by summation of K or K naught. Okay, and K naught If consider this is a frame structure, okay, this is one of the frame structure, this is hinge support. Okay, so here the support is A, this is B, and C and O. Okay, L is a length, EI is the flexural stiffness, L is a length, EI is a flexural stiffness, L is length and EI is a flexural stiffness for all the three members. Then K naught is equal to summation of stiffness at member, summation of stiffness at member meeting at joint, okay. So first member OA, so take it as KOA, stiffness of OA member, stiffness of OC member, stiffness of OB member. Okay, so take this joint or O joint as a center, and from this O the A support is fixed, means far end is fixed here, so the K value, stiffness value is 4 EI by L plus KOC. Okay, in case of OC member the far end is free, then the stiffness value is equal to 0, plus in case of OB the far end is hinge, then the stiffness value is 3 EI by L. By adding this we get 7 EI by L, and this 7 EI by L is nothing but a stiffness at joint, okay. The individual value about the end condition is stiffness of member, and addition of all the stiffness at members is nothing but stiffness at joint. Then distribution factor. Distribution factor is represent like this, DF. DF is a ratio of stiffness. DS is a ratio of stiffness at member to stiffness at joint. This is the formula to calculate the distribution factor. Okay, DF is equal to K divided by summation of K or K naught. Okay, the moment in case of stiffness is always distribute in opposite sign. This is the important point from this formula is stiffness at member to stiffness at joint. This is how you can calculate the distribution factor. Carryover factor is a ratio of moment transfer at far end to moment transfer at near end. Okay, this is the carryover factor, ratio of movement transfer at far end to movement transfer at near end. In that 4 conditions are there. First condition, if far end is fixed, okay, so the movement transfer at the far end is half. Okay, so if this is the beam, and here the, for example, here the moment act is m. Okay, for example, here the moment act is equal to m, then moment transfer on this end is m by 2. Okay, so this is how the carryover factor works. Then next, if far end is hinge or roller, then moment transfer or the carryover factor transferred is 0. Then third is far end is free. Here also carryover factor is equal to 0. Then fourth condition is when internal hinge is present. Then carryover factor is equals to MB by A. Okay, this is the value. If A is equal to B is equal to L by 2, then the carryover factor is equal to 1. Okay, so this is how you can calculate the carryover factor for different beam or frame conditions. And the carryover factor transferred with the same sign. Carry or factor transferred with same sign, but moment transfer with opposite sign. Okay, this is the important point. Carry or factor transfer with same sign. The next point is relative stiffness. Relative stiffness is a ratio of stiffness. Relative stiffness is a ratio of stiffness divided by Young's modulus of elasticity. In that first condition, if far end is fixed, then the relative stiffness is equals to, for far end the stiffness is 4 EI by L divided by Young's modulus. Then value of relative stiffness for far end is fixed is 4I by L. Then second, far end is hinge or roller. Far end is hinge or roller. Then the relative stiffness is equals to, here the stiffness is 3 EI by L divided by Young's modulus 3I by L. This is the value of far end. This is the value of relative stiffness when far end is roller or hinge. Then third is far end is free. Far end is free. The value of stiffness here is equal to 0. So total relative stiffness value after calculation we get 0. Okay, so these are the relative stiffness values. And last condition is if internal hinge is present. If internal hinge is present, if this is the beam and in that beam internal hinge is present, A and this is B distance, then the relative stiffness is equal to, so this is the formula to calculate the relative stiffness, 3I A square divided by A cube plus B cube. And if the internal hinge is present at center, then A is equals to L by 2 and B is also equal to L by 2. Relative stiffness for that condition is 3I by L. If you put the values of A and B into this equation, you get the relative stiffness values. If internal hinge is present at center, then the relative stiffness is 3EI by L. The next point is fixed end moment. So the fixed end moment point is covered in the previous video, which is in short notes of strength of material. So in that video I cover a chart related to fixed end moment. In that I go for many of the conditions of beam with different loadings on that beam, and there we calculate a fixed end moments. But there are two fixed end moments or two settlements in case of fixed end moments we are not discussed in that video, so we discuss here. So the fixed end moments due to settlement of supports are fixed end moments due to settlement of supports are first condition, if this is fixed beam, okay, this fixed beam is settled down up to this point, up to delta, okay, then the moment for this fixed beam about MAB, this is support A, this is B, and about moment BA is equal, okay, and that value is equals to 6 EI delta divided by L square. Okay, moment for both ends is same, that is 6 EI delta by L square. Then next, if far end is hinge and that hinge support is settled down, then the value of moment at AB is equals to, this moment is equals to, this is support A, this is B, and that value is equals to minus of 3 EI delta by L square, 3 EI delta by L square. But in case of moment of BA, that value is equals to 0. So these are the values for the settlement of supports. Then slope deflection method. So in the slope deflection method, there are two type of equations are formed. In that first is joint equilibrium equation, and second equation is shear equation. Okay, these are the two type of equations here. So here the number of joint equilibrium equations are equals to number of unknown rotation, and in this the number of shear equations formed, here number of joint equilibrium equation formed is equals to number of unknown rotations, and here the number of shear equations formed are equals to number of unknown displacement. Okay, so here we consider one example to differentiate a difference between joint equilibrium equation and shear equation. So this is one example. This is a frame with fixed support. Okay, this is A, B, C and D. So here joint equilibrium equations are required in number 2, or two joint equilibrium equations are required to solve these kind of a frame, because two supports are there or two joints are there except the supports, and here one shear equation is required to solve this beam. So first we know about the joint equilibrium equation. So in that, at joint B, the joint equilibrium equation is MBC plus MBA is equal to 0, and at joint C, MCD plus MCB is equal to 0. So this is the joint equilibrium equation, and shear equation is MAB plus MBA divided by L plus MCD plus MBC divided by L is equal to 0. So these are the shear equation and joint equilibrium equations for solving these kind of frames. Then next is the slope deflection equation. So here this is an example of a frame with fixed support at both end and a 1 point load on the span, which is P, and the slope deflection equation for span AB and BA is, so here the MAB is equals to MAB bar plus 2EI divided by L into twice of theta A plus theta B. Then moment of BA is equals to MBA bar plus 2EI divided by L in bracket twice of theta B plus theta A. So this is how you can calculate the span, or this is how you can calculate the slope deflection equations for span AB and BA, and the same equations for span BC and CB, then for span CD and DC. So you can calculate the values of these span like this. Okay, just replace the value of A with B for this, and here B with C. Then to calculate CB, replace this B with C and this A with B. Okay, this is how you can calculate the slope deflection for the remaining span too. Okay, so here we end with a syllabus of theory of structure completely as a short notes. And okay, so